Oh, it's time. Maybe I should just start. Okay, so there were some interesting questions at the end last time, and so I thought I would just briefly mention some things related to those questions. So last time I was discussing n equals 0 SUNC gauge theory with NF fundamental and anti-fundamental flavors, and I'm taking them to be massless. We could first study the theory where they're massless and then study what happens when we turn on the mass terms. So if NF is bigger than 11 halves NC, the theory is not asymptotically free, and so at RG flows in the infrared to a free theory, and we need some kind of UV completion. And I wanted to write down the value of the conformal anomaly A in this case. So A, in this case, it's the A of the infrared free theory. We can just compute the conformal anomaly in free field theory. And so the result from free field theory is there's some normalization factor, which is the value of A for a scalar. So here this 0 is for a scalar. And then each gauge field contributes 62 times that. So there's 62 times the number of gauge fields. And each Dirac fermion contributes 11 times that. So there's plus 11 NCNF. Okay, so that's the value of A in the infrared in this case. Now, in the case where we're within the conformal window, so here NF is between 11 halves NC and some lower bound for the conformal window, which it's not known what it is, and this is something that's studied on the lattice, for instance, then the theory is asymptotically free in the ultraviolet, and the RG flows like this to a conformal field theory. So here we have some infrared conformal field theory. And A in the, now we can use the same expression A for the ultraviolet fixed point. So here we'll say this is A in the ultraviolet because it's the same free field calculation in the ultraviolet. And so this is what we know. It's in ultraviolet free. And then according to the A theorem, it's bigger than the A in the infrared conformal field theory. And the A in the infrared conformal field theory is some function of NC and F, which if we're very close to the upper bound of this conformal window, we could try to compute it in conformal perturbation theory. But in general, it's not known. So this is known, and this in general isn't known. But this is the inequality that we expect from the A theorem. And then as we add, now we could study renormalization group flows where we could turn on mass terms. And so we can add masses and integrate out flavors. So if we start from some value of NF, we can use this to reduce NF. And then we have some kind of renormalization group flow, for instance, where we have some CFT in the ultraviolet that's labeled by NC and NF. And then we could have, for instance, like a RG flow to a CFT in the infrared, where NC stays the same and NF goes down by 1. So we could have these kinds of RG flows. And again, now we would say that A of the UV should be bigger than A in the infrared. And here in general, we don't know how to compute either one of these, but this is some inequality that we expect to hold. And then at some point, something else happens, and so one thing that's believed to happen at some value of NF is chiral symmetry breaking. And what happens here is the SUNF left times SUNF right gets spontaneously broken down to the diagonal SU and F. And this happens by a non-zero condensate of psi tilde. And so in this case, the low energy theory, let's write low energy effective field theory, isn't anymore described in terms of the conformal field theory or the original degrees of freedom. Instead, it's described by the nonlinear sigma model for this. So we say that this is our group G, this is our group H, and so we have Nambu, Goldstone, boson, pions in the coset G mod H. And here we know what the value of A in the infrared is because it's a free theory. As we go towards the infrared, these are these Goldstone boson pions. So let's write here Nambu, Goldstone, boson, pions, chiral Lagrangian. And so here we know the infrared theory just because we believe that this chiral symmetry is broken and there are these massless Goldstone boson pions. And this is a nonlinear sigma model on this group manifold. And this nonlinear sigma model is infrared free. So in this limit, we could compute the value of A in the infrared. And it's just given by these, whatever we choose, the normalization for a free scalar times the number of scalars, which in this case is the dimension of this group manifold, which is an F squared minus 1. And this thing, by the way, has to be less than this thing that we would compute in the ultraviolet theory. And so that doesn't give any interesting constraint on NF. Okay, so this is in fact, this is easily less than A of the UV free. So this is a renormalization group flow in this range where both the ultraviolet and the infrared theories are free. The ultraviolet is free quarks and gluons, and the infrared is free pions. And we could compute in this case A in both limits and see that the A theorem is satisfied. And so one of the questions was when does this happen, and is it calculable when this happens? And so the lore is that this happens when the dimension of this operator psi tilde, which is a gauge invariant operator, and classically in the ultraviolet its dimension is 3, and then the lore is that this happens when this is equal to 2. And the unitarity bound for this, by the way, is 1, because this is a scalar operator, so the unitarity bound has to be bigger than 1. Okay, so yes?
Is there an explanation for that lore?
So if you look in terms of the, if you try to write down like a effective field theory for the pion fields, then you see that at this point there's like a tachyonic mode, which makes them want to have a non-zero expectation value. But
I can compute that quantity in QCD, and it's never much different from 3.
right. So in the so what happens in the ultraviolet? So for instance, in this case, what you would find if you computed this in perturbation theory is that it would be 3 plus some anomalous dimension, and that the anomalous dimension is turns out to be negative, the anomalous contribution from the gauge interactions. And as you increase this NF, it becomes more and more negative. And at some point, I mean, people have tried to calculate this in QCD, like Applequest and company got this estimate that this happens when NF is 4 NC but yeah, I know you're shaking your head. I don't want to.
I mean, in actual QCD, if they can calculate it on the lattice this, we clearly have chiral symmetry breaking, and if it's nowhere near to an actual QCD, then it's not. Maybe in other theories, if it gets to 2, there's chiral symmetry breaking, but it doesn't seem like it's required for chiral symmetry.
That's right. That's right. Yes, I completely agree.
Is it a coincidence that it's D over 2?
Hmm?
Is it a coincidence that it's D over 2?
No, I don't think it's a coincidence that it's C over 2. Yeah. Yeah. All sorts of interesting things happen when you have an operator whose square is kind of like is what you would think is being like a marginal operator. And then you can have like these trace squared operators. And all sorts of interesting things happen also in the supersymmetric case when operators hit that point. Okay, and so one of the questions that I wanted to mention a little bit about was why didn't I refer to this as a confining phase? And so just one brief point about that is that as long as NF is non-zero, there isn't confinement in the strict sense, because if we look at like a Wilson loop, or if we think about like some sources with a Q and Q bar and this kind of flux tube, then if there are massless fundamentals, as we separate this farther and farther apart, eventually you can pop a quark and an anti-quark out of the vacuum, and then the flux tube can break. And so if NF is bigger than 0, there's no order parameter or confinement. And in fact, you could smoothly go in between different phases, like a Higgs phase and a phase that looks sort of confining. And but now the NF equals 0 case is special. So now the flux tube can't break, and so there's a discrete one-form symmetry associated with the center. Which we can use to assign charges to like string excitations, like these kinds of string excitations. And now there is an order parameter for confinement. And so it's believed, for instance, in so in the infrared, we get a gapped confining phase with this symmetry unbroken. And so I was trying to decide in my lectures how much of this to discuss also in the supersymmetric context, because in the supersymmetric context we can also discuss the case NF equals 0 and things related to this center symmetry, and maybe I'll mention a few things about it, and maybe I don't know if Yuji was planning to talk about some of these kind of mixed anomalies in the SUSY Yang-Mills. No? Okay. I might mention a few things about it. Much of this stuff is due to 2 of the other speakers in this week. So, okay, let's see. Is there anything else I wanted to say? Maybe I should ask if there are any questions. No? Okay. Yeah, so I wanted to now start to talk about the supersymmetric theory. So SUSY advantages. So in the supersymmetric theory, we have some additional tools. And this is related to Nadi's discussion yesterday about kinematics versus dynamics. So in the supersymmetric theory, we have a bigger symmetry group, and so we kind of expand the range of kinematics. And so there are some things which we can determine essentially just by kinematics. which otherwise would be very hard calculations to determine by dynamics. So there's more kinematics information. And so the main example that I wanted to discuss is SUSY QCD, and I already wrote the symmetry table over there. But before discussing that example, I thought I would just say some generalities. So one aspect of supersymmetric theories is that they often have, in fact, very often they have classical moduli spaces of vacua. And this is something that Clay talked about in his lectures, about how if you have, for instance, a supersymmetric gauge theory like SUSY QCD, what we could do is we could give expectation values to the scalar components of the matter fields. So these classical moduli spaces are where some scalar component of a chiral superfield is non-zero. And if this scalar component of a chiral superfield is in some representation of the gauge group, this leads to like a Higgs mechanism of the gauge group. So we give expectation values. For instance, if we're discussing SUSY QCD, we can have matter fields in the fundamental and the anti-fundamental. Those matter fields are in chiral superfields. The bottom component of the chiral superfield is a scalar. And then in supersymmetry, you can give expectation values to bottom components. Without breaking supersymmetry. So without breaking supersymmetry, we can give an expectation value to the scalar component of these chiral superfields. And this could lead to, for instance, like a Higgs mechanism. So this Higgs is the gauge group. And so a nice thing about this is that this helps us, this tells us right away that there are what some of the light fields are in the infrared theory. Because the fact that we have this moduli space of vacua means that at least classically we have massless fields. And so those massless fields, they could be lifted by some quantum effects. And that's something that we could try to study. But basically we know that there's a low energy effective field theory of these moduli. And we can identify what those moduli are. Like we can just write down what are the components of the fields that we have, and we can see what these moduli are. So that's a little bit like this case of the Goldstone bosons, where sometimes they are associated with spontaneously breaking global symmetries, and so they're Goldstone bosons, but that's not always the case. So we have this space of moduli, and then we could try to write down an effective field theory for that. And a nice thing about that is that on this space of vacua, so here I'm discussing again 4D n equals 1 SUSY, for instance. And so we have this moduli space of vacua. And one way to describe the moduli space of vacua is the set of solutions to the D-term equations, modulo gauge transformations. Or another way to, maybe I should have written here. It's the set of expectation values of all the fields subject to setting the d terms to 0 and then modding out by the gauge transformations. Or we could write it as the set of expectation values of the various scalar fields modded out by the complexification of the gauge transformations. Or, so this is something that Clay discussed. Or we could write it as the set of expectation values of the gauge invariant composites modding out by any classical relations. I should say these are the classical moduli spaces of vacua, and then we can ask what happens in the quantum theory. Okay, so there are these various different ways of describing them. And so these are complex spaces. Like here, these gauge invariant composites would be composites that we make from the chiral superfields, and their scalar components are complex. And so these are some complex spaces. And so yes, thank you. So the question was, what about the superpotential and constraints from the F term? And so here I'm taking first with W with 0 tree-level superpotential. So here to begin with, I'm considering the case where we turn off this tree-level superpotential. Then we get this then we typically get these moduli spaces of vacua, and then we can ask what happens when we turn on the tree-level superpotential and how that affects it. And then we have to impose, indeed, the F-term conditions for this superpotential. Yes, thank you. So these are complex spaces. And certain and some quantities have to be holomorphic in their dependence on these complex moduli. And this is also something that maybe I'll go over here. This is also a review of something that Clay discussed. So for example, we could write down the so let's call these complex moduli fields X. So we'll have some low energy effective field theory. And in this low energy effective field theory, we'd like to study some dynamics. And so one of the things that we could study in terms of dynamics is a dynamically generated superpotential, for example. And so this dynamically generated superpotential will be a function of these moduli fields X. So these are the moduli, classical moduli. And then it can also depend on various coupling constants in our theory. And so let's call the coupling constants some G. So these are some coupling constants that we might have. And if these coupling constants are coupling constants in the superpotential, then they should also be thought of as background expectation values of chiral superfields. And so for superpotential couplings, this superpotential can depend on those things, but it has to depend holomorphically. So the point that I'm getting to is that it's holomorphic in both the fields, the coupling constants, among the holomorphic coupling constants, by the way, is the dynamical scale lambda of the gauge theory to, let's with some coefficient that's related to the one loop beta function. And this is something that also that Clay discussed last week, that if you look in the if you look at the one loop running, what you get is e to the minus 8 pi squared over g squared of mu plus I theta is e to the 2 pi I times what people sometimes call tau, complex modulus, and this is lambda over mu to the coefficient, which is the one loop beta function. And so we could use this tau here in the superpotential, but it's more natural to use this combination, as I'll discuss. Okay, so one of the tools that's very important is the fact that this is holomorphic in the xi's and the g's. And especially important is the fact that if we take some of these xi's to be large, if we go very, very far away from the origin on the moduli space, often that's a weakly coupled limit. And the reason for that is because these xi's so if this xi spontaneously breaks the gauge symmetry, so let's say if it Higgs's the gauge symmetry, then we could think about that as we're, if I plot here as a function of the energy scale, let's say this is the energy scale, then, so this xi is some gauge invariant composite, but it's associated with some charged matter field. Getting some expectation value. And so at very, very high energies, we have our original gauge group. Let's call the original gauge group G. And so this is our ultraviolet gauge group. And then below the scale of this expectation value, some of the components of G get expectation values. Some of the components of G get masses by the Higgs mechanism. And so sometimes I'll just refer to those as being like the W bosons. So we have some massive gauge fields that are like W bosons, and we can integrate them out. There might be something left over that could be some other subgroup that we could call it H. And so these are some light fields, remainders. And then what you find when you look at the behavior of the beta function is that if the theory is asymptotically free, this low energy theory is more weakly coupled than the original theory. And so the infrared theory is more weakly coupled. Let's say it's weaker. And so often we could think about, as we go far from the origin on this moduli space of vacua, that's some limit where we have a better control of the theory because it's more weak coupling. So I'll give examples of this in the context of SUSY QCD. But so this is one of the tools, is that we have this moduli space of vacua. We know in some limit it becomes more weakly coupled. And then we could try to write down what's the dynamical superpotential as a function of these moduli and coupling constants. Any question? Okay, Another special advantage of supersymmetric theories, especially in the conformal case. So let's say here if we have a super conformal field theory, then in the case of a super conformal field theory, we could look at the multiplets of operators, which are highly constrained by the superconformal algebra. And this is something that Leonardo will discuss more about in his talks, Leonardo Rastelli, about the multiplet constraints in superconformal field theories. And but the one thing that I wanted to emphasize is that one multiplet that we always have is the stress tensor multiplet. So T mu nu sits in a multiplet. And in these superconformal representations, T mu nu always sits at the top of the multiplet. This is something I think Clay also discussed in his last lecture, that in order to get the right supersymmetry algebra, the stress tensor has to sit at the top of the multiplet. And then we can ask, what's the operator that sits at the bottom of that multiplet? And in the case of n equals 1, so for 4D, n equals 1, a conserved U1R current is at the bottom. So Clay in his lectures discussed R symmetries and how it's a symmetry of the algebra, but the theory itself might or might not have an R symmetry depending on what terms we have in the superpotential and what other interactions might violate R symmetries. But if it's a superconformal field theory, it has to have an R symmetry because the multiplet structure requires a conserved R symmetry. So in a superconformal field theory, we have this conserved R symmetry, J R mu, that's related by supersymmetry to T mu nu. And so when we label multiplets, we can label multiplets by or representations of the superconformal algebra by the spin under the left under SU2 left of the Lorentz group, the spin under SU2 right of the Lorentz group, the dimension of the operator, and the R charge. So this is the U1 R charge. This is the operator dimension, and these are the spins. And then there are various unitarity bounds, which I think Leonardo will discuss these unitarity bounds. And when the unitarity bounds are saturated, these multiplets have some null operators, and so then we say that they're short multiplets. And so short multiplets include, for instance, the stress tensor is in a short multiplet. Anything that has a conservation law is in a short multiplet. So because the stress tensor is conserved and the R symmetry is conserved, this is in a short multiplet. Conserved currents are in short multiplets. Chiral superfields are in short multiplets. And so in particular, let's say that if we have a chiral superfield, that's a short multiplet because Q bar annihilates it. And that requires, if it's a scalar operator, the dimension of the operator is 3/2 times the R charge of the operator. This R charge of the operator is also what I call here little r. Okay, so the nice thing about this is that if we can identify this R symmetry that sits in the same multiplet as the stress tensor, then we know the dimensions of chiral operators by this relation. And so this gives us exact, if we know the R symmetry exactly, this gives us exact information about the operator dimensions. So this will happen, for instance, in this SUSY QCD example that I'll get to soon. We know the what the R charge has to be in the conformal field theory, and so then we can write down exact operator dimensions using this property of the algebra. Another nice thing about this connection between the R symmetry and the stress tensor is in terms of the quantity A. And this is something that I'll discuss much more in the next lecture. The A and C, so in a superconformal field theory, the A and the C anomalies are related by supersymmetry to linear combinations of U1R cubed and U1R at Hooft anomalies. So I'll write down the specific the explicit formulas probably in the next lecture, but I just wanted to kind of give a broad overview of some of the advantages of supersymmetry. So because at Hooft anomalies are often nicely calculable because they're constant along renormalization group flows. So because these things are constant on renormalization group flows, if we have, for instance, asymptotically free theory, like QCD below the asymptotic freedom bound, SUSY QCD below the asymptotic freedom bound, then we could compute these at Hooft anomalies in the ultraviolet, where the theory is asymptotically free and it's weakly coupled. And so we can compute these exactly. Then they're constant along the RG flows, and so those have to be the same values in the infrared conformal field theory. And then we can get the exact answers for A and C in the infrared conformal field theory. So this is unlike the non-supersymmetric case that I mentioned, where we don't know how to compute those things. Here we can compute them exactly. So we can often get them. Okay, I think maybe that's enough for the moment about generalities, and then I'll discuss more, unless there are any questions, more the SUSY QCD case. Okay, so this is the supersymmetric version of the QCD theory that I wrote down last time. So n equals 1 supersymmetric QCD. We'll take the gauge group to be SUNC, and then we have NF fermions that are now chiral superfields, and usually these are called Q, which is kind of confusing because Q is also the supercharge. For the moment, I put the flavor and color indices here, but I'll drop them, and then it will really look like the supercharge. But the supercharge has a spinor index. So these are chiral superfields. They're in the fundamental of SUNC. There are NF of them, and so there's an SUNF left that rotates them. Then for gauge anomaly cancellation, we include the same number NF of antifundamentals. So now there's no gauge anomaly. There's a separate SUNF that rotates those ones. And just like last time, there's a baryon number symmetry. Last time I normalized the baryon number symmetry so that a baryon had charge 1. Now I'd like to change notation and just say that the Qs themselves have charge 1. It's kind of how I normalize the generators for this, but it's kind of nicer to take the generators to act with charge 1 here. It doesn't really matter. Then there's this U1 asymmetry that I mentioned last time in the case of QCD. And now here I added the R symmetry. And so I'll discuss a little bit more about this R symmetry. But this, just as a preview, this R symmetry will be the same R symmetry that plays this role in the superconformal field theory of giving us exact operator dimensions and exact values for A. So that this R symmetry will kind of play some starring role in a lot of the things that I'll discuss today. Now we could look at gauge invariant operators, and so we could form, for instance, mesons by making Q and Q tilde composites. So this is a meson. It's gauge invariant. I just add the different flavor charges. So I'm just adding the charges of Q and Q tilde. This S is a glue ball superfield. So the first case that I'll discuss will be the case NF equals 0, and then I'll say some things about this glue ball superfield. But this glue ball superfield, I'm kind of including it because I want to say some things about it, but it's not going to be a light field in the low energy effective theory. So when I write down the low energy effective theory, maybe I'll put like a little line through this thing, but eventually I won't include that in the low energy effective field theory. And then this is this holomorphic version of the gauge coupling that I mentioned, this lambda to the 3 and C minus NF. And I'm assigning charges to that because, I guess I erased it, but maybe it's here. So this e to the minus 8 pi squared over g squared plus I theta, it's lambda over mu, and the coefficient is the one loop beta function. And the one loop beta function in this case is 3 and C minus NF. So this is the analog of this 11 halves NC minus NF that I wrote down before. And okay, so this is the relation between the running G and the dynamical scale mu. And this combination, e to the minus 8 pi squared over g squared plus I theta, this is e to the minus instanton action. And so this is the thing that multiplies the 't Hooft vertex. And this 't Hooft vertex is the thing that I mentioned last time that has some fermion zero modes that we can read off from the Atiyah-Singer index theorem or from the triangle diagram. And so maybe I'll write here. So we have the instanton. And so I'm going to picture this instanton as being some kind of interaction in Euclidean spacetime, which has some fermion zero modes. And so just like last time, we have one fermion zero mode for each fundamental and anti-fundamental flavor. So we have psi 1 up to psi NF. And now we have psi tilde 1, psi tilde NF. So this is like what I had last time. But now there's a new element because the gauge fields are related by supersymmetry to gauginos. And so we need also fermion zero modes for the gauginos. And so the gauginos I call, or people call lambda. So we have gaugino fermion zero modes. And the number of these fermion zero modes, we always can read off the number of these fermion zero modes from the quadratic Casimir of the representation. And so we normalize it so that it's 1 for a fundamental. And then if we compute it for the adjoint, so T2, where the representation is the adjoint, it's equal to, in general, 2 times, sometimes people call the dual Coxeter number of the group G. And for the case of SUNC, this is 2NC. Okay, so this H is NC for SUNC. For other groups, you can compute it, like for E8, it's 30. And so these are some gaugino zero modes. So this instanton at hoof vertex, again, just like in the QCD case, it violates the anomalous symmetry. So there's an axial U1 symmetry that tells us that some linear combination of these different U1s. So here I wrote down three different U1s. One linear combination of these three U1s is violated by the anomaly. And so here I chose these three U1s so that only this one is the one that's violated by the anomaly. So let's just check that the other ones aren't violated by the anomaly. So here, under baryon number symmetry, the Q's have opposite charges and the gauginos are neutral. And so the psi's and the psi tildes cancel each other off. So this thing is neutral under U1 baryon. And okay, so this is neutral, and that's why I wrote here 0 here. So this is the instanton factor, the instanton at hoof vertex factor, and I'm going to give it charges associated with that, with the fermion zero modes for that anomaly. And so here it has charge 0. By the way, it's neutral under the gauge group, and it's neutral under the non-abelian flavor symmetries, just because those things can't have any ABJ anomalies. The ABJ anomaly again comes from a triangle diagram with a flavor, gauge, and this is we get a factor of the trace of the generator in this flavor symmetry, and so it can only be non-zero for U1 symmetries. So, like for instance, it's gauge invariant because these things, their gauge charges cancel. This is some gauge invariant combination of these adjoints. It's invariant under SU and F flavor because there's an epsilon tensor that contracts these, and so you get all NF of these fully anti-symmetrized. So it's invariant under SU and F left and also under SU and F right. Okay, so that explains all of these charges. And now I should explain why it has this R charge. And the reason for that R charge is that U1R symmetry a U1R symmetry has to assign charge 0 to, it's a phase rotation. It has to assign charge 0, of course, to the gauge fields because we can't rotate the gauge fields by some complex phase. So the R charges of the gauge fields are 0. And if we look at how the gauge fields sit in a multiplet, that tells us that the R charge of the gauginos, so these are in the adjoints, has to be 1. And then also if the R charge of some chiral superfield, let's say that we have some chiral superfield that we'll call it X, is R, then the R charge of the fermion component of X. So this is a scalar which is at the bottom of the multiplet, and then we get a fermion component by acting with the supercharge. And if we're careful with the consequence of that, what we get is that this is equal to R minus 1. So the fermion has charge. We subtract 1 from acting with the supercharge. Mm-hmm.
Are you normalizing so that your supercharges have plus minus 1?
Yeah, so the supercharge Q actually acts to give here this one, and we give it charge minus 1. Yeah, it's a little funny, but that's the way that it's usually chosen. Okay, sorry, just to repeat the question. The question was what are the charge assignments for the supercharges, and do we give the supercharge Q charge minus 1? And yes, we're giving it charge minus 1. Okay, so if we go, so that's the reason for this 1 here. Because if we look at now the R charge for the fermion components of these guys, the fermion components, their R charge is just minus NC over NF. And so if we add up all of these U1 charges here, we'll see that these ones contribute U1 charge to NC. And now these ones we're going to assign some U1 R charge to cancel that 2NC. And so since there are 2NF of them and we're going to give them all the same R charge because we want the R symmetry to commute with the flavor symmetries, we want we want to assign R charge minus NC over NF to each of them. Okay, so the R charge of psi okay, and then that will cancel to be A, B, J, anomaly free. We could get the same statement just by looking at the triangle diagram. So we're trying to cancel the triangle diagram where we have the U1R symmetry here and the gauge fields here. And so this is 0 when we add up all of the contributions of the gauginos and the matter fields. So this is a conserved R symmetry. On the other hand, this axial U1 symmetry, oh, why did I write 2? This should have been 2NF. Yeah, because so under this axial U1 symmetry, we have the 2NF squared. And 1 over g squared in the action is the coefficient of this operator S. So if we write down in the action, this thing appears as the gauge kinetic terms. Its coefficient is 1 over g squared. And so we could always think about, like when we study the 1 pi effective action, we have the sources and the operators. And derivatives with respect to the sources brings down the operator. And so I want to think about this lambda to the 3nc minus nf, which is basically like 1 over g squared, as being the source for this operator in the effective action. And so here, this W low has the property that if I take a derivative of this with respect to log of lambda to 3nc minus nf, I get these values of s's. So here, if I take d by d log of this, you can check that it gives those values of s's. The nc here just cancels the thing that I get from taking this 1 over nc. Okay.
Question?
Yes.
You told us that lambda doesn't have any UMR charge. How come S and W could have some UMR charge too?
Yeah, thank you. Yeah, so the question was about the UNR charges. Yeah, so in general what happens is that we'll have a superpotential which has some coupling constant and then the associated operator. And we want the U1, and so then I'll say here that d by dg is going to bring down a factor of this x when I act on it when I act with it on yeah, so basically, if I take what I mean by this is that if I take d, yeah, maybe I should write it more explicitly. So d by dg of w effective of g is going to give us the x expectation value. So what we can see from both of these is that the r charge of g plus the r charge of x should be 2. So here this thing has r charge 2 and this thing has r charge 0. And so that fits with that. And so the superpotential is r charge 2, and then when I take the derivative with respect to g, I'll get here the r charge of this x. So yeah, so basically this is how they should add up.
But you're taking the derivative in lambda, right?
Yes. So
Doesn't have any UMR charge still.
Yeah. Okay. Yeah. So actually, I should say here that in this table where I said that lambda has r charge 0, this is an R symmetry that we can write down for any nf that's non-zero. For nf equals 0, we can't write down this R symmetry because this R symmetry gave charges to the size that had this 1 over nf. So this R symmetry just doesn't make sense in the nf equals 0 case. In the nf equals 0 case, all we can do is we can say lambda to the 3nc has r, right, so yeah, thank you for that. So r charge of lambda to the 3nc for, so this is in the nf equals 0 case, is just the r charge of this hoof vertex, which is 2nc. And the fact that this R charge is non-zero tells us that the R symmetry is broken down to Z2NC. Yeah, so that's related to the fact that there's no R symmetry actually in this case. Gosh, I didn't get to SUSY QCD duality. Okay. Yeah, maybe I'll just press on and some of the SUSY QCD duality I guess we'll spill into the next lecture. Okay, so now let's consider the case NF non-zero, and want to write it like this. So for the case where NF is bigger than 0 and less than NC, then our light fields are the meson fields. And so the classical moduli space of vacua is the set of all expectation values of these meson fields, the set of all expectation values of these meson fields. And so the complex dimension of this moduli space is NF squared, because these flavor indices can run from 1 to NF. And we can also understand the NF squared as coming because the gauge group is broken from SUNC. When these get expectation value, the gauge group was broken from SUNC down to SUNC minus NF generically, because we're giving each flavor sequentially can Higgs the gauge group by 1. So if we give expectation value to one fundamental and anti-fundamental, we can Higgs down to SU and C minus 1, and then we just keep doing that until we get to SU and C minus NF. And then by the Higgs mechanism, we could count the number of chiral superfields by a supersymmetric version of the Higgs mechanism. And so the number of fields should be, originally we had 2 and C and F matter fields. These are the Q's and the Q tildes. And then we should subtract the number that were eaten. And so the number that were eaten are the number of broken generators here. And so we start off with NC squared minus 1, and then we break it to NC minus NF squared and let's just check that the coefficient of NF squared works. So we have minus is plus NF squared. Yes. So right. So this tells us that these moduli we could think of as being like the components of the matter fields that are left uneaten after the Higgs mechanism. Okay. So that's the case if NF is less than NC. And topologically, this moduli space is just the complex plane to this power. And so that's a smooth space. The actual classical metric on that space, the classical metric on that space is singular at places where the gauge group would be unbroken. So we could write down a classical metric for the meson field. And singularities in the effective field theory always arise when there are some extra massless fields. And so we know what to expect. When these fields that we said were eaten by the Higgs mechanism actually aren't eaten by the Higgs mechanism, there should be a singularity. And that will show up in the classical metric on the moduli space. Okay. For the case of NF is bigger than or equal to NC, then generically SUNC is completely broken. And we can also form in addition to the meson fields, there are baryon fields. And so just to give an example of that, if we look at the case where NF equals NC, then we have Q with a flavor index and a color index. And we could just contract the flavor and color indices with epsilon tensors, which is like taking the determinant of that matrix. And so this is the operator that we'll call B. And there's a similar operator called B tilde involving Q tilde. And now if we compute the dimension of the moduli space, we could again get it from the same counting. So it's 2 and C and F minus, now all of the generators are Eden. And so that's the classical dimension of the moduli space. And if we count on the other hand, the number of mesons and baryons, we'll see that there are more mesons and baryons. And so what that tells us is that this moduli space has some constraints relating the mesons and the baryons. And so for example, in NF equals NC, the classical moduli space is given by the mesons FG tilde, the baryons, with a constraint which is zero, because the baryon is the determinant of Q and the meson is Q tilde. And so if I take the determinant of this matrix, I just get the product of those determinants. And this illustrates how for general NF bigger than NC, this is a singular space. And the reason why it's singular is because I could satisfy this constraint and also the derivative of this constraint being 0. And so whenever you have a situation like that, there's something which is like a conical singularity. And so we could picture the moduli space as having some kind of singularity. And the singularity requires some new degrees of freedom. So the classical answer for what those new massless degrees of freedom are is that it's just back to the original matter fields of the original theory that we had, because this was assuming some kind of Higgs mechanism, and at these places where the singularities are, that's exactly where some of the fields that we would have thought are massless by the Higgs mechanism actually aren't. In the quantum theory, we can have completely different massless degrees of freedom there, or it can be smoothed out. And so basically,
We're about 3 minutes over.
oh, okay,
Finish up.
okay, yeah, sorry. Yeah, so I guess I'll say the answer next time in terms of Seiberg duality for this theory. So when we write down Seiberg duality, it will tell us in different cases what are these new massless degrees of freedom, when there's a conformal field theory, what the superconformal R charges and anomalies are for that superconformal theory. And yeah, so sorry to go over, but I'll leave that all to next time.
We can get some coffee and then maybe come back and ask kind of questions as we write a couple of.
Okay,
Thank you.
thanks.
I have a, like in the it's like a mismatch parenthesis.
Oh,
So missing square.
this whole thing was in parentheses.
Wait, no, but like the bottom entry.
The bottom left line.
Oh, no, it's not a two. Okay, never mind.
Oh, sorry. Yes. That's
I think also this too is.
yeah. What am I doing?
Okay.
That was a bad typo. Thank you.
I have another
Uh-huh.
question. So, I think at one point I don't quite agree with Clay's point. Also, your point. You say that the for expression maybe and phi could be expectation of group